Today I want to spend some time talking about PCI Bus. And following today's lecture, we're going to look at DMA and interrupt in more detail. But today we're going to focus on the first part, the Peripheral Component Interconnect, or PCI. PCI is a very popular interconnection within a computer system. It's virtually the only bus found in the new system. Okay. Although new systems really have PCI Express, but PCI is the origin of the PCI Express bus. It has replaced many older buses, for example, ISA and VESA buses. One of the nice features of PCI bus is the plug-and-play characteristics and the ability to function with 64-bit data bus. A PCI interface, which we'll look at, consists of registers, and these registers located in a small memory region. And these registers in this region contain many important information about the device. By device, we mean, for example, a network interface card or a video card. These are the devices we refer to here. And many of such devices have the PCI or PCIe interface, which are used to connect to the motherboard. And that's how you build a system with not only processors and memory, but also many different kinds of devices. And with this PCI interface and the necessary information describing the characteristics of a device, we can have the ability to recognize these devices automatically by either the BIOS, the basic I/O system of the motherboard, or by the operating system. And that's why this PCI and PCI devices have the plug-and-play feature. Because of this PCI interface has a set of registers that describing the device, we are able to recognize them and configure them. And that's the reason PCI and PCI Express has become very popular interconnection. This is a simplified picture showing the architecture of these different buses within a computer system. From the microprocessor, it may or may not have this off-chip cache. Then this microprocessor and the cache will be connected to the memory subsystem on so-called the local bus or front-side bus, using Intel's term. This bus is high speed, running at sometimes over gigahertz, and this bus will be connected to the PCI bus through a bridge or bus controller. And on this PCI bus, you can have all these different kinds of devices. In this example, we have a video graphics card, we have this controller, and we can even connect this bus with other buses through another controller, sometimes called a bridge chip. This is what I just mentioned. The resident local bus is the high-speed bus connecting microprocessors and memory subsystems, and we use bridge chips to interconnect two different buses. This is another view of typical PCI system, very similar to what we just saw. This is the CPU and RAM. We have a host bridge, and this host bridge is often implemented as a chipset. If you heard of the chipset term, that's the combination of a number of different controllers inside the same chip, and this chip, the chipset, is connecting the microcontroller and other interconnection systems. In this example, it's a PCI bus. And between this PCI bus 0 and PCI bus 1, we can have a bridge to interconnect them. And on these buses, these are the different devices that we can connect. PCI bus functions with 32 or 64-bit data bus and a full 32-bit address bus. And these address and data bus are often multiplexed to reduce the size of the controller connector. For a 32-bit data PCI card, it has 62 connections on the connector, and for a 64-bit PCI card, it has 94 connections. Now, besides these address bus and data bus connections, PCI bus also use a large set of control signals. That's why you see these many bits altogether. A PCI card with 64-bit data can accommodate 64-bit address if required at a future point. This is the picture showing the actual signals out of the 62 or 94 pins. We normally use PCI to interface peripheral devices to the microcontroller. Memory could also be interfaced, but the operation speed is very slow. For example, this PCI 2.1 operates at 66 megahertz, and for older ones, it operates at 33 megahertz. PCI address appears on the multiplexed data line through AD0 from AD0 through AD31. And this address is multiplexed with data, as we will see in the next slide where we show the timing diagram. And some systems use 64-bit data bus, so the upper 32-bit from AD32 through AD63 are used for data transfer only. And these pins can be later used to extend the address to 64 bits. In the next slide, we're going to see the timing diagram. And in the timing diagram, you will see the addresses are multiplexed with data and control signals for multiplexing. So this is the clock. It could be 66 megahertz or 33 megahertz. And we have this address data bus. As you can see that at this T0 to T1, we're putting the address on the bus. And in the next few cycles, that's where we send out the data. So the same bus, we are multiplexing it for data and address. And we also have a set of control signals to send out commands and also to send out the byte enable signals. In the next couple of slides, we're going to look at the configuration space. Configuration space is the set of registers we mentioned at the beginning, and these registers store important information of a device. PCI contains 256 bytes of memory, in fact registers, to allow the computer system, could be an embedded system, to interrogate the PCI interface. And this feature allows the system to automatically configure itself for plug and play. The first 64 bytes we'll see in the next slide in more detail, contain information about the interface. What kind of information? For example, who is the vendor of this device? And what's the type of this device? Is it a graphics card or is it a Ethernet controller? What is it? And if it is, for example, an Ethernet controller, then what's the model? Okay, this is from Intel, but Intel produced tons of such similar interface. What's the model number? What's the ID of the product? So that's we're going to see in the first 32-bit out of this 64 bytes. The first 32-bit double word contains the unit ID code and the vendor ID code. This picture shows the PCI configuration space. As we said, that this configuration space has up to 256 bytes. So that's why you see the address from 00 to FF. And we use the first 64 bytes to store important information. The first 32-bit word, starting from address 00, this is the identification, which includes the vendor ID and the device ID. The next double word, we have the command, the status information. And then we have class. This class field represents the actual type of this device, whether it's a graphics card or whether it's a Ethernet controller. And starting from 10, we have a set of registers that's used to store the base address, or BAR registers. And we have other fields for example, actual ROM address and some reserved field. This picture gives you more detail about this configuration space. We only show the first 64 bytes here. From address 0, the first 2 bytes are the vendor ID. And the second 2 bytes are the device ID. Then we have the command register, status register, etc., and the revision number. And then we have this class code. Okay. And we have other parameters. And then we have this base address 0, base address 1, etc. This base address 0, base address 1 are going to be written by the BIOS, the basic I/O system of the motherboard, or by the operating system. The purpose of these addresses is to store the starting address of the components or resources of this PCI device. Because a PCI device, for example, Ethernet controller, the way the Ethernet controller works is it receives packets from the wire. If it's a wired interface card, it'll put to a small buffer within that controller, within that card. Once that card is full, the buffer is full, it will push that received packet over the PCI bus to the host memory. To know the size of the buffer, to understand the status of the buffer within that PCI interface, we need to map that resource into the host address space. Because for the CPU, it only knows about its own address space, from 0 to 4 gigabytes or larger if it is a 64-bit. So whatever resource presented by the PCI device, if you want the host CPU to access that resource have to be mapped to the address space. of the host. Could be memory address space, could be I/O address space. So that address, the base address, is going to be stored in these registers. For the unique ID code is a 16-bit number. For the class code is another 16-bit number starting from address from at location 08. And we can also find the vendor ID, etc. Now I'm going to show you the actual device presented in one of the computers we have. This is a Linux machine, so I log into the machine, and then I can execute this lspci. Let me do this, lspci. So this command lists the devices, PCI type of devices, connected to this system. As you can see, we have a lot of things. We have a host bridge. Okay. This is actually a bridge between the PCI bus and the USB bus. And we have USB controllers. We have another PCI bridge. We even have an ISA bridge. We have here an Ethernet controller. Okay. So this command tells you high-level information about what do we have in this system. Now, how do I know? Well, how does the system know that I have such Ethernet controller device? It's because each PCI device has that first 64 byte of configuration information. It stores the IDs of these devices. The vendor ID, device ID, the class ID is a multimedia audio controller or is an Ethernet controller. That's the class we're talking about. So next command I'm going to execute is this. Okay, this is to say that I will want to look at the actual configuration bytes of this device 01:0C. You don't have to worry about the .0. And I want to look at the detailed information. So if I execute this command, okay, it'll give me a lot of details. We know this is an Ethernet controller, and we know that this is from Intel, okay, and the model of this controller is 82540EM. This is a gigabit Ethernet controller. It also shows that I have two regions. Okay, region 0, the memory is starting at this address, and region 2, it's an I/O resource, and the address starts at DF40. Okay, still mystery. How does the system know about this? How does this Linux box know about this address here and that model number? These 4 lines below show you the actual 64 bytes or in that PCI configuration space. So let's look at this. The first 2 bytes, if you remember the table I just showed you, the first two bytes represent the vendor ID. Okay? And this is a little endian, so we're talking about 8086. Okay. Every vendor, let's say Intel or AMD or NVIDIA, they will have their own device IDs, and these IDs are managed by the PCI SIG organization. That's the authority to assign these IDs. and 8086 is the ID of Intel. So we know, okay, this is the device manufactured, designed by Intel. And the following 2 bytes, 100E, this is a device produced by Intel. So Intel has the authority to assign these codes to their devices. And by checking their database, the device, the operating system finds out that this is a gigabit Ethernet controller. This is the particular model. If you look at further, this 0200, these 2 bytes represent the class. This is an Ethernet controller. All the Ethernet controllers will have this 0200 as its class ID. Okay. Now, what about these ones? How do I know that I have some resource available on this particular Ethernet controller, and starting with this address, and this resource is mapped to my host system starting from that address? If you look at this here, this is actually bar address 0. Okay, this FEAE00, this is the value stored in the first bar register, and that's to say that I have some memory resource available, and that memory on the card is mapped to my host memory starting from this address. And the next one, the I/O ports starting from DF40. Okay, that's this here. In fact, these 4 bytes. DF41. Now, you said, why is 40 there and 41 here? It turns out, in fact, the last bit of the bar register indicates whether this resource is a memory resource or is an I/O resource. If you have a 1 there, that's an I/O resource. That means the address, this DF40, is an I/O address rather than a memory address. So that's why you see the region 2, which is this is bar 0, bar 1, and bar 2. Region 2 is an I/O address, and it starts at DF40. Okay. Yes.
The cache, they mentioned the cache instructions showed in the PCI.
Yep.
What's some kind of connection with this main system cache?
So there's still a lot of more information in the configuration space. One of them is to say whether the device, the resource, is cacheable or not cacheable. There are a lot more details you can look into when you look at the spec of the PCI configuration space. So we just saw the example of the actual PCI devices presented in the system, and we look at their configuration bytes and to figure out how the OS will understand what kind of device it is. This is to explain again the base address. The base address could be an address in memory or an address in I/O space. It's differentiated by using the least significant bit of the bar register. Typically, Intel architecture uses 16-bit I/O address space, but there's room for expanding to 32-bit I/O addressing using these bar registers. The other 2 words is status and command, which is located in the second double word of the configuration space, and the details are here. I won't go through each of these individual pins, but what you're gonna understand is it will use the PCI device use these two registers to report the status and also to receive commanding from the operating system. Okay, we saw in the example that that particular Ethernet controller has been assigned address, one for the bar 0, that's a memory address, and for bar 2, that's an I/O address. But who assigns these addresses? It's the BIOS does the job. Modern BIOS in the computer system, one of its functionality is to scan the buses. It will interrogate the devices on the bus to understand what they are and also to decide which address should we assign to these individual resources available in the devices. And you can also call these BIOS functions by using interrupt vector 1A. In the textbook, there's a table lists the functions available through the DOS interrupt, and you can use these functions to, for example, list the devices, interrogate the resource available of the particular device. And in the next slide, I will show a short program in assembly language that demonstrate how the BIOS is used to determine whether the PCI bus extension is available or not. The BIOS, in combination with the operating system, will perform the configuration transactions with every PCI device. The purpose of their work in this stage is to allow safe space allocation for each of these devices. Also, it'll map the memory or I/O regions to the processor's address space. This is an example where we use one BIOS PCI functions. By moving this 0B1 to AH, we're gonna use one of the functions of this PCI command presented by the BIOS. This int 1A is to call the BIOS to execute these PCI related functions, and this B1 is the particular function we will need to use. The return value of that function, in this case, we're going to use the carry bit. This carry bit represents whether the BIOS function detects the existence of a PCI bus or PCI device. If we do have a carry bit, that means we have a PCI bus. It'll then call this int21 to display this message. Otherwise, we'll display the message PCI bus is not present. PCI interface, we use PCI controller because, as you can see, that there's a lot of information needs to maintain, and PCI device has to respond to the commands coming from the host computer. In the next slide, we have a diagram that shows the components that by design are inherent to this PCI interface. To summarize, we have these following components in the PCI interface: registers, parity checking block, initiators, target, vendor ID, EPROMs. Those are required components of any PCI device. So the diagram is here. We have these several bar registers. We have these vendor ID, device ID information, which are stored in EEPROM. And we have this parity checking circuit, we have initiator circuit, and we have target module to generate necessary control signals for communicating with the bus and with other components in the PCI subsystem. So what we're trying to say here, these are the components that are necessary on any PCI device, being either an Ethernet controller or graphics card. For any PCI device, you need to have these components. After PCI bus, people have been trying hard to improve the performance, as PCI bus has its limitations on the bus speed. But still, at the same time, because the advantage of PCI bus is the plug and play. With this configuration space, we can essentially easily put in different peripherals into a computer system, and they will work very nicely together, because the BIOS and the OS will handle all the resource address allocation. We still want to keep that, but at the same time, we would like to improve the performance. So after PCI, people have designed PCI Express Bus. Although they share the name PCI, but in fact, this PCI Express Bus transfers data in serial. PCI bus transfers data in parallel, because you have those 32-bit or 64-bit data bus. For PCI Express, it's actually transferring serial data, but very fast. It transfers serial data at 2.5 gigahertz compared to the legacy. And for one pair of serial data, transmit and receiving, it can support up to 250 megabytes per second. Okay. But on the other hand, a standard PCI device delivers data at only about 133 megabytes per second. The way we define or design the PCI Express bus is that we call each serial connection a lane. That's why when you buy a PCI device, the newer, say, graphics card, there's one spec on the box saying how many lanes this card requires. 4 lane or 8 lane. That's to say how many such serial connections we have for that particular device or the slot. For example, a main motherboard could have maybe 4 one-lane slots, and with each lane transfers 250 megabytes per second. You're talking about overall, you can transfer 1 gigabytes per second with those 4 lanes. Another example, a modern video card, it may have 16 lanes, which can transfer data at speed of 4 gigabytes per second. Okay. The PCI Express standard allows up to 32 lanes, but most of the products available have 16 lanes. Most motherboards contains 4 single-lane slots for devices that do not require speed over 250 bytes per second. And for video cards, especially for the high performance video cards with graphics processor on it, they require 16 lanes per slot. PCI Express goes through several generations. Now it's generation 4. The data list on this slide is for the older generation, generation 2. It can transfer the data at 500 megabits per second per lane. And PCI is replacing many of the older interconnects, such as AGP ports for the video cards. Because these PCI bus transfers data using serial connections, it greatly reduced the number of connectors. For the older PCI bus, PCI devices, you need to have 62 or 94 pins on a connector. And here we're talking about much less, because you have only 2 serial lines for one data transfer. But on the other hand, as we said earlier, we want to maintain or keep the benefit of this plug and play feature. So PCI Express Bus still supports the PCI configuration space. So the first 64 bytes, the way it organized this first 64 bytes is the same. It has the vendor ID, device ID, class ID, etc. It also has those bar registers to allocate addresses for resources available on the device. And this picture here shows the one example. This is, I believe, it's one lane connector, and it uses 3.3 volts on the PCI Express bus for signaling, for controlling data. And the lane is constructed from a pair of data pipes, one for input, one for output. So basically, receive and transfer.